So let's look at this problem. A 40 ml sample of 0.1 molar nitrous acid is titrated with 0.2 molar KOH. Calculate the pH at the equivalence point. And we're given Ka for the acid, 4.6 times 10 to the minus 4. It's always a good idea to write a chemical equation, right? So what's going on here in the reaction between these two guys? We've got HNO2 plus KOH, and that's going to react to form KNO2 plus H2O. What do we know about the relative quantities of acid and base at the equivalence point? They're the same, or they're the stoichiometric values, right? So this is a 1-to-1 ratio, so it'll be the same. So we could look at 40 milliliters of 0.1 molar nitrous acid. Well, let's just organize this here. 40.0 milliliters. This is 0.100 molar. And this is 0.2 molar. Do we need to figure out the volume of KOH added? We actually do, because to calculate the pH at the equivalence point, we need to know the total volume of the solution. So here I have 40 milliliters of 0.1 molar. So 40 milliliters of 0.1, we'll do millimoles per milliliter, and that's the acid. And then we've got 1 millimole of KOH to 1 millimole of the acid. And then we're going to go to milliliters of the KOH solution. So the KOH is 0.200. There are other ways to do that calculation, but that's the preferred method. Because if it's not a 1-to-1 ratio, you will catch it. So 20.0 milliliters. So we know that we've added equal molar amounts of the KNO2 and the KOH. Well, what are the moles or millimoles? So it's 4 millimoles, right? 4 millimoles of acid, 4 millimoles of base. Yeah? I did not plan this out well at all. So we got 4 millimoles of that, and I saved that one. 4 millimoles of this. And after that reaction occurs, what do we have left?
4 millimoles of each product.
So yeah, 4 millimoles each of the products, right? Because these are at the equivalence point. So we're going to end up with 4 millimoles of KNO2. do we actually need to know anything about that potassium?
Yeah.
No, potassium is just the escort. So this is NO2 minus the conjugate base of a weak acid, right? So we'll look at how that behaves as a base. So this is the equilibrium reaction for that. What's the equilibrium constant for that reaction?
Maybe.
Kb. We were given Ka. Kb equals 10 to the minus 14 divided by Ka. Um, 2.17 times 10 to the minus 11. So up here, we were thinking about stoichiometry and moles reacting. When we're doing an equilibrium calculation, we need molarity, right? So we've got 4 millimoles of this in a total of how much? What's the total volume there?
20 plus 40 milliliters.
Yeah, 20 plus 40. We got 20 plus 40, or 60 milliliters. This is just a mess. So the NO2 concentration is going to be 4 millimoles divided by 60 milliliters. .0667. What's the initial concentration of HNO2? So this is where we have to think, well, what do we mean by initial? Which initial, right? So the way you view a titration like this is the acid and the base react completely to form the NO2 minus. And now we're going to take that as our new starting point and see how it reacts back. Okay? So we made a bunch of this, 4 millimoles of it. But because it's the conjugate base of a weak acid, it's going to react with the water and produce a little bit of the nitric acid. So we're thinking about after the titration reaction goes completely, what do we have? Well, we have 0.0667 molar NO2 minus, and what concentration of HNO2? 0. Mm-hmm. And for the hydroxide, we say approximately 0. Then we can continue with our changes here. I guess I should put pluses there. I'm just doing X is small. came up with that. Which is 0.002%. So is X small? Yeah, X is super small. How's this going to help us find the pH of the solution? Because X is equal to the concentration of hydroxide ion, right? So we could calculate the pOH, negative log of 1.2 times 10 to the minus 6, or 5.92. And then pH is 14 minus 5.92. Which is 8.08. Is that kind of what we expect for the titration of weak acid? Yes.
Yeah.
Because at the equivalence point, when you're titrating weak acid, the solution will be somewhat basic because you have that weak conjugate base in there. Any questions? There's lots of different scenarios, lots of different questions that can be asked. So we need to have an understanding of, okay, what's reacting? Where do I have to think about equilibrium? Where can I just think of completely reacting? I keep KB, Ka separate, and there's a lot of little pieces. 8.08. So here's one without a calculation. So we've got two 25 ml samples of unknown monoprotic acids, and they're both titrated with 0.1 molar sodium hydroxide solutions. We've got the pH titration curves here. Which of the two weak acid solutions is more concentrated? A. So this is the equivalence point, right? And that tells us the volume of sodium hydroxide added. So there it's just under 35, and over here it's less than 25. So that tells us that this one's more concentrated because the equivalence point is further over on that milliliters of sodium hydroxide added. So acid A is more concentrated. Which of the two weak acids has the larger Ka? So this one's harder to think about. We just did a calculation where we calculated the pH at the equivalence point. We could look back at that and see, well, if the Ka was larger, what would that do to the pH? That sounds a little painful. We could also think, well, what's the pH of a strong acid at equivalence point? 7. What makes a strong acid different than a weak acid? It ionizes completely. So basically, I gotta stop using that word in this chapter. Essentially, you could think of a strong acid as having an infinitely large Ka, right? So if I have a bigger Ka, I should be closer to 7. Does that make sense? Because it's more like a strong acid. So this one looks like it's around 10. This one looks around maybe 8.5, 9.
They look the same.
Well, they do look the same until you actually identify, okay, whoops. There's the middle, right? And there's the middle. Okay, so this one's at 8. Wait, not 8. This one's at 9. Dang. You're so right. What the heck? Well, what would that tell us? Not the amount of acid. The Kas are the same. The Kas must be the same. It could be the same acid. Just one's more concentrated than the other. Obviously, I did not look at that answer before class. Yes.
Can we base ourselves with the pKa? pKa, the acid and the base is the same. So therefore, half of the equivalence point should be half of the volume use.
Yes. And now that you mention that, that's actually what we're supposed to do. Oh, just thinking creatively. Okay, so as Nestor pointed out, this is the buffer region, and this is the buffer region. At the half equivalence point, the pH is equal to the pKa. Somehow, I just completely forgot that. So half of about 35 is around here. And that's like half of 24, so that might be around here. Are those the same? No, they're not. I'd like to say I went off on that other tangent, just to show you a wrong way of thinking. No, I just went down a rabbit hole. It was kind of interesting, though. We can, turn it around and make it useful. The difference in pH at the equivalence point is very small, and so, as it turns out, that doesn't really work. The pKa is the pH at the equivalence point. So pKa of 6 is 10 to the minus 6, right? pKa of, well, we could just call it 5. That's Ka, right? This pH gives us the pKa. This is approximately, very, very approximately the Ka. Which one's bigger? B. So this one has the higher or larger Ka. Any questions?
So we can't use the equivalence point as a judgment for which one has a greater Ka, or is this just in this unique case for both reasons?
I think what I accidentally demonstrated here is that when you're just looking at a graph and eyeballing where the equivalence point is, the difference here in the pH is within your error of eyeballing it. So if we actually, did the calculations with the slope and everything and found that, I'm sure they would be different in the right direction, but it's not significant enough for us to use that. It's a good idea, I think, but it didn't work. So when we get to the exam for this chapter, there could be questions like that. They're asking you to look at a titration curve and get information out of it. Yeah.
I'm kind of
Okay. I'm sure several other people are as well. So if the pKa is 5, it's a little less than 5, right? Then the Ka is equal to 10 to the negative 5. Because Ka is equal to 10 to the negative pKa. In the same way that pKa is equal to the negative log of the Ka. It's the same relationship as pH.
Right, so. I guess I'm confused on how we're relating pKa to this plot of pH. Or are we just substituting in pKa?
So what we're doing is we are remembering that at the half equivalence point for a weak acid, the pH is the same as the pKa. So, we can take the volume here, which is like maybe 34, and come up with 17 or whatever here, and draw a line over. It's kind of crooked, but it gives us the idea. And then here, we're going to the half equivalence point. That was maybe 23 or 24, so here's like 12, and we're finding out what the pH is.
Is this gone over in chapter 18? Wherever that pKa is the half equivalence point, I missed that somewhere.
I think that's in chapter 18, yeah,
Okay.
in an earlier section.
Okay.
Yeah. And that's one of those things that's just easy to overlook, right? So it's good that you asked about it. So what about the titration of a weak base with a strong acid? Well, again, it's just the reverse. So the calculations are really similar. Up here, you're going to have a buffer region. At the half equivalence point, you've got equal molarities of the weak base and its conjugate acid. And you get your equivalence point as we're coming down, and the solution ends up acidic. So you can calculate the pH at the half equivalence point, or if you've got the pH at the half equivalence point, you can calculate pKa. But you have to use pKa for the conjugate base, not pKb. Because that being equal to the pKa comes from the Henderson-Hasselbalch equation.
Right.
Because at half equivalence, they're going to be equal,
Ratios.
right? There's equal ratio. We've pushed it halfway over. So when these are equal, this term goes to 0. But this does not work with pKb. Could you derive an expression that works with pKb?
Yeah.
Yes, you could. But there would be another thing to remember. And all you need to do is change pKb to pKa, and you're good. And that subtract from 14. It's not that hard, right? So the Henderson-Hasselbalch equation always uses pKa. What's the pH at the half equivalence point in the titration of a weak base with a strong acid? pKb of the weak base is 8.75. Well, what did we just talk about?
Can't use pKb.
We can't use pKb, we need the pKa. But it's easy to find. pKa is 14 minus 8.75, which is 5.25. So in this titration of the weak base, at the half equivalence point, the pH is equal to the pKa. Any questions?
Wait, so you have base in there and you're putting acid onto it?
Mm-hmm.
Why is it so low? For half equivalence.
Oops. I need to do that. I think because, so the PKB, there's the clear button. So if I actually calculate the PKB here, I'm sorry, the KB is 2 times 10 to the minus 9. And the Ka, which we could also calculate this way, I think the reason is because this weak base that we're titrating is super weak, right? It's really more of an acid. It's the conjugate acid is stronger than the weak base. But that's a good question. So what about polyprotic acids? Diprotic or triprotic? So here we're going to look at sulfurous acid being titrated with sodium hydroxide. And we have sulfurous acid losing 1 proton, and that has a Ka, and losing a second proton, and that has a Ka, which is smaller. If the Kas for the 2 steps are sufficiently different, you will get 2 equivalence points. If they are too close, though, it'll just kind of merge together and just kind of look messy. The volume needed to reach the first equivalence point is the same as the volume needed to reach the second equivalence point. Because here you've titrated the first proton off of everybody. And when you get over here, you've titrated the second proton off of everybody. Okay, consider these 3 titrations. Here we've got the volumes and concentrations are the same for everybody here. So here we have a monoprotic weak acid, and they're all being titrated with a strong base. Here we have a diprotic weak acid, and here we have a strong acid. Which statement is most likely to be true? All 3 titrations have the same initial pH. Is that going to be true? No. The strong acid is going to have a lower pH than either of these guys because the strong acid dissociates, it ionizes completely. So that one's wrong. All 3 titrations have the same pH at their first equivalence points. No, because a strong acid is pH 7, weak acids are higher than that. All three titrations require the same volume of sodium hydroxide to reach their first equivalence point. That's true. Because we have the same volumes and same concentrations. So to reach the first equivalence point, we have the same number of moles of acid, so it'll take the same number of moles of sodium hydroxide.
That's only if they're 1-to-1 ratio, right?
That's a great question. That's if there's a 1-to-1 ratio. This one there is a 1-to-2 ratio. But this is talking about the first equivalence point. So the first equivalence point is the same. The second equivalence point will take another amount equal. It'll be twice as much. So if you look at the final result, this guy is going to take twice as much sodium hydroxide. But they're the same here because we're just talking about the first one.
If their KAs is like way too different from one another, right? Or did I call it?
Yeah, if the KAs are different enough that you can actually distinguish where that is, yeah. So monitoring the pH. So what we did in Chem 1A is we used an indicator. We used phenolphthalein. And so as we titrated, the solution was clear, and then it would begin to turn pink, and if we kept going, it would be more of a fuchsia color, right? So the indicator will change color in a range of pH, right? You can't use the same indicator for everything, because if you have something that has what's it called? If the pH at the equivalence point is down here, that's not going to work for you because you're going to go past the equivalence point before you get to the pH where phenolphthalein changes color. What's really nice about the indicators is they're very low tech, right? You just need a burette and some solutions and you're good. You can also use a pH meter. And we'll be doing that in one of our experiments. So what are these indicators? There's a whole bunch of them, not just phenolphthalein. These indicators are weak organic acids where the acid is a different color than the conjugate base, which is really kind of crazy when you think about it. You put a hydrogen ion on it and it changes color. Cool. And they are very intensely colored, so we only need a tiny bit. If we needed a bunch, they would also participate in the titration and mess up our results. So they have to be very intensely colored. So this is the structure for phenolphthalein. In an acid, it's colorless. In the base, it's pink. So yeah. And here we see phenolphthalein in solutions of different pH. So 4 and 6, it's clear. At 8, it's beginning to turn pink. A little bit of it has turned pink. At 10, there's more, and 12 is like, woohoo. So the pH at which the indicator changes color depends on the pKa of that organic weak acid. And they're going to change color within a range of two pH units. So 1 pH unit on either side of their pKa. It's not like, oh, I'm going to get to 7 and now it's suddenly going to change color, right? It's going to go gradually over a range of 2 pH units. So here we've got methyl red, and here we've got pH 2, pH 4, pH 5. 7, 9, and 10, right? And so we see here, it's still orange, and here it's yellow. So when your pH is 1 above the pKa, you see the color of the basic form of the indicator. When the pH is 1 unit below the pKa, you see the color of the acidic form. And this is a table showing ranges of color change for several acid-base indicators. So think back to Chem 1A, and you're titrating like KHP with sodium hydroxide. What did you think the pH was at the equivalence point? 7, right? Was it 7? No, it was higher than 7. When we go to look at phenolphthalein, which is down here, phenolphthalein begins to change color around pH 8.5, which is fine for a weak acid. But this would not be the best choice for a strong acid where your equivalence point is at 7. You'd be better off with something like phenyl red. Why do these guys, this one here, alizarin and thymol blue, why do they have 2? They're diprotic, right? So their color changes once when it's monoprotonate, or when it loses 1, and it changes color again when it loses another one.